A key concept in cosmology is look-back time, the idea that distant light is ancient light. Light takes time to travel through the voids of intergalactic space, so we see distant objects as they were and not as they are. This concept was encapsulated in the introduction to the movie Contact, although there was alteration of the time scales involved, which you can notice.
Clearly, I've never been there, but this feels like
situation. Obviously a major malfunction.
the president's a crook. Well, I'm not a crook.
Robert Kennedy was shot in that ballroom.
A sniper has fired at President Kennedy. Communist Party. Or have you ever been a member of the Communist Party?
Never done.
For something never before experienced. 1941, a date which will live in...
And we continue this season's final edition of our Maxwell House Good News of 1930. Walter Winchell, good evening, Mr. North American. All the ships at sea. Let's go to press.
If the speed of light were infinite, then we would see everything in the universe as it is right now. In a sense, this pileup of information would be confusing. It's been said that time is nature's way of stopping everything from happening at once. In fact, light travels very fast, imperceptibly fast, on human scales and on terrestrial scales. But in the cosmos, we notice the time that it takes light to travel, and this leads to look-back time. We see distant parts of the universe as they were, and if they're far enough away, we look back over significant fractions of the age of the universe. This is not a problem of measurement or experimental technique, it's a fundamental limitation of physics caused by the finite speed of light. We see the sun as it was 8 minutes ago, objects in the outer solar system as they were hours ago, nearby stars as they were a decade ago, the most distant stars to the naked eye perhaps as they were centuries ago, and the nearest galaxies as they were hundreds of thousands or millions of years ago. Astronomers know how to turn lemons into lemonade, and so rather than being a limitation, this is an advantage. This means we can use distant objects to see back in time and to see how the universe evolved to its present state. When we look at the beautiful spiral pattern of our nearby neighbor in space, the Andromeda galaxy M31, it's tempting to ask the question, what is Andromeda doing now? What does it look like now? This is not a question we can answer with observation. We are stuck seeing old light from Andromeda. We are stuck seeing things that happened on Andromeda 2.25 million years ago. As time moves forward, we see more and more recent events but always with that time lag due to light travel time. This leads to some interesting conceptual issues. Let's imagine a galaxy that's further away, still easy to observe with a large telescope, 100 million light years away. We see that galaxy as it was 100 million years ago, not as it is now. Suppose we see a star in that galaxy that goes off as a supernova while we observe with our telescopes. Measurements of this star show that it's 10 million years old as we observe it. And we know from these measurements that it's a type of star that lasts for 50 million years as a main sequence star before it detonates as a supernova. So, we see the galaxy as it was 100 million years ago. And as we see it, the bright star within it is 10 million years old and will have a total lifetime of 50 million years. The question is, has the supernova event already occurred? And if so, when? The answer is 60 million years. The galaxy light is 100 million years old, and the star is 10 million years old as we see it. It lives for a total lifetime of 50 million years, which means another 40 million years required before the star dies. But with 100 million year old light, that event took place 60 million years ago. We'll just have to wait 60 million years to see the supernova go off. These are the conundrums and paradoxes that seem to result from light travel time. But if we accept that we're looking at ancient information, we can learn a lot about the universe. Conceptually, we have the nearby now. When we look at stars, we see them as they were decades or centuries ago. And in cosmological or geological terms, that's very recent. We see galaxies as they were long ago, tens of millions of years, certainly longer than the age of the human species. So light from those galaxies was emitted before humans even existed. And then the distant universe is the ancient past. It's easy to see galaxies, even with modest-sized telescopes, whose light was emitted before the Earth formed, a third of the universe's age ago. And with the biggest telescopes, it's possible to see galaxies whose light was emitted 12 or 13 billion years ago, when the universe was 5 or 10% of its present age. Lookback time results from the finite speed of light. Light travels at 300,000 kilometers per second, so its travel is imperceptible on terrestrial scales or human scales. But moving out into the universe, the time it takes to travel becomes significant. We see the nearby parts of the Milky Way as they were hundreds or thousands of years ago. We see nearby galaxies as they were millions of years ago, and we see the most distant galaxies as they were 5 or 10 billion years ago, a substantial fraction of the age of the universe. This notion of look-back time, that distant light is old light, allows us to turn telescopes into time machines and look back and see how the universe evolved.